All right, good morning. This is the start of the recording. I am just trying to check on a thing on screen. I don't know where it is. Okay. Oh well. Well, we'll make it work. All right, hello. It is Tuesday, April 28th at 7:45 a.m. And let's see. We'll do. Come on. I hope this is connected. So I had some battery issues in my last class yesterday, so hoping everything here works out. We'll see how this goes. Today's a Tuesday, so there is an online quiz. Please complete that. There is a math is a process assignment due Wednesday. The instructions for the assignment are the same as in previous math is a process pre-exam assignments. But I noticed there was a missing PDF for the instructions, so I posted that in there. Um, Thursday there is an exam. That's the date of the exam anyway, but you can choose any 5 hour window of time on either Thursday or Friday. But in particular, there will be no meeting live on Thursday morning. Um, the one key difference, other than of course there's new content since, but the key formatting difference is I would like you to turn in a single PDF file, one PDF file with all the questions that are in order in the PDF. However many pages you need to make your PDF, that's fine. But there are within the exam for info and other places, I've posted some instructions on or tools that you can use that are like some free apps that will get you through that. I would suggest that you start WebWork 40 or thereabouts today instead of sometimes it's too easy to fall back towards just the one that's to start the one that's due today, but that will lead to frustrations. And there's the office hours as a reminder. So um, the main new thing that we looked at yesterday, and the thing that I want you to practice today, is if you're given a function. I've stated this just ever so slightly differently and provided a new picture. So given a function, y equals f of x, and two x values, so x equals a number a and x equals a number b, then the definite integral is the signed area between the graph of the function and the x-axis. So between those two things, the graph of your function always passes a vertical line test. So you've got these two kind of horizontally pieces, right? With the x-axis being a straight horizontal piece, and then the vertical line test passes on the graph of your function, like maybe it's this function. So those are sort of the two kind of horizontally pieces, and we're gonna have to cap the ends off somehow, and that's what the vertical lines x equals a and x equals b are about. So yeah, that's what the definite integral is. Um, so there were different pictures provided yesterday, but here using this function that kind of dips just slightly under the x-axis just for a moment, using this x value called a and this x value called b, there are now three shaded regions. There's this bigger positive shaded region, there's like a medium-sized positive shaded region, and there's this tiny bit of space under the x-axis, and that will be counted as negative area. Yeah, so in this example, with this function as an example, that we had three different pictures as examples yesterday. three cartoon pictures. In this new fourth cartoon picture, there's two big positive areas and one small negative area. So overall, the area in this picture should be positive because it's much more positive area than negative area. This concept of signed area is a little strange at first, but it's the thing that's going to make what we do tomorrow and Monday after the exam and so on. It's going to make it all work out a little better. So yeah, we have signed area. I'd like to try a handful of practice problems that look, some won't look quite the same as yesterday. So let's take a look at this one first. So the definite integral from -1 to 5 of 4x dx. So the function here is f of x equals 4x, or y equals 4x. That's the function. The first x value, or the endpoint as it's called, is -1, and then the other endpoint is 5 in this example. So that generically in the cartoon just a moment ago, the -1 and 5 were called a and b. So we'll draw a picture of this. So y equals 4x is, that's a y equals mx plus b, where the m is 4 and the y-intercept is 0. So this is a line of slope 4 that goes to the origin. So that the graph of the function is this slanted line there of slope 4. The x values of -1, sorry, how it's running into things here, but x value of -1 and x value of 5 are listed there. And when you draw in those vertical lines, you end up capping off two regions. So there's this region drawn in yellow above the x-axis, and then this smaller region below the x-axis that I've shaded in red. Since the x value here is 5, the y value of 20, we're going to need we need the area of this rectangle, so we need both the base and the height. The base we can see is going to be 5, but we need the height. And so the height of this rectangle is given by this line segment here that I'm tracing over. But that, right at that intersection, that's actually a point on the slanted line. So we can get that point by plugging in 5, this x value of 5, into the function. So that's, yeah, where do the y coordinates, like this y coordinate of -4 and this y coordinate of 20, where did they come from? Well, f of -1 is -4, and f of 5 is 20. So using the coordinates, all these tick marks labeled, we can see now this first, the bigger triangle is a positive area, and the area is half base height, so 1/2 times, and then the base of 5 and a height of 20. Okay, so that's, that just for reference later, if people are looking at the slides without the recording, that's shown in yellow. There is a smaller area that is negative of 1/2 times base times height. Now the base is 1, so if you start right here at the origin and you need to get to right there, if that's tick mark -1, then it takes 1 unit. We're just counting this all positive for a moment, and then we'll stick the minus sign in at the end. But that length is 1, and then this length, the vertical length this way, has to be 4, because you're starting right, let me erase this so I can rediscuss, right? So you're starting here, let's say, to get the height of this small triangle, and right where this thick dot is drawn in, the y coordinate is 0, and then if you move, you've got to move 4 units down to get to where the y coordinate is -4. So that's where this height of 4 came from. So we have 1/2 base times height there, but that will be counted as a negative area, and you'll see this as it's all put together. So this original question, it is about signed area. We end up with the positive area, I just copied this right there, minus, because we have a negative area, 1/2 times 1 times 4. And I just went ahead and simplified the arithmetic here as a 48. I would not be expecting this, not expecting people to simplify that arithmetic on the final. So, but I hope that works as just sort of first of all, a reminder example of this signed area concept. So there's a positive area and a negative area. I have, I'll wait for a moment, make sure we're okay. I do have a couple other examples I want to try that are a little different. Well, sorry, I got one more that I want to try, and then I want to give you a chance to work on some of these. Wouldn't it be 38? Maybe I may have screwed up the arithmetic here. Let's see. So 20 canceling with the 2 is a 10, so that's 50, right? And then 4 divided by 2. So 50 here minus 2. I think it is 48. Let me erase all that. Right? Because wait, did I do something wrong here? Let me I now need to double check here. So another way to do this would be 5 times 20 is 100, and then half of 100 is 50. So this first part is 50 here. Yeah, let's see if oh, okay. Sorry. Yep. All right. Sorry. Was looking at the wrong chat. Okay. All right. So okay. Yeah, and see that's the thing. So if it's just some arithmetic, it's not the kind of thing that I want people to even worry about, bother with for a quiz or exam. So I just the purpose of putting the number 48 here is because we will reuse this at the end of class for a quick thing, and so I just thought it's just a little more convenient to have a number than to have all this. So, all right. Sorry, I had a battery run out on another device, so I had to kind of switch things up, and I'm using a pen that I don't really quite understand yet. So here, the next example has something a little strange going on in it. The function is now well, it's right here as usual. But the function, so that there's two x values, -2 and +13. But the function is f of x equals absolute value of x minus 3, or if you want, you could call it, y equals absolute value of x minus 3. Now the thing to do here is how do we graph this kind of thing? It's think about the graph of y equals absolute value of x. So I'm hoping that's one that you had looked at previously in an algebra class, or just as a reminder that this shape would be a V that looks like this. There's a 45-degree angle there and a 45-degree angle there. And then this -3, that's a -3 directly affecting the x coordinate. And you can, it's a reminder of some old ideas, but that a -3 ends up being a shift to the right. So you end up with a graph that looks like that. It turns out that if the slope here is 1 and then the slope on this other half is -1, then for the slope to be -1, this y-intercept here would have to be a 3. So here's a cleaner picture of it. So I hope that reminder of things is helpful, even if a little rusty. Graph transformations, it's sort of like, actually, one of the things I remember saying at the beginning of the semester, I don't know if you remember it, might have freaked you out for a moment, was that in Math 175, in calculus, you end up using just about everything learned in an algebra class. We have not done a whole lot of graphing, actually, but everything else, solving equations, manipulating fractions, we've seen a lot of that stuff. There's some graphing aspect that we haven't really looked at much yet, and it's not that I'm incorporating because I just want to cover all the algebra. It's just it really is, there's, so anyway, so here's the graph of that V shape. Okay. And because we're talking about y equals absolute value of x minus 3, you'll notice, when you absolute value a thing, you never get a negative. The smallest number you can get is 0. So this entire graph is above the x-axis. I mean, maybe not above right at x equals 3. It touches the x-axis. But the point is, the graph is never below the x-axis. So I kind of moved the axes around so that you could see. And if you're a Vikings fan, I'm sorry for the color choices this time around. Okay. So where do we get, again, the y coordinates of 5 and 10? Where did they come from? The usual thing here, right? So our function is f of x equals absolute value of x minus 3. So when you plug in this x value of -2, which was provided, into here, you end up with absolute value of -5, which is +5. And then when you plug in the other x value of 13 into the function, you get absolute value of 10, which is +10. So you get, because we were absolute valuing again, so your y values are 5 and 10, they are positive. And so that point right there has x coordinate -2, y coordinate 5, and this point has x coordinate 13, y coordinate 10. And this should all be kind of all the details we need in order to find the area, right? So for instance, now both triangles are considered positive area because they're above the x-axis. So this triangle right here, 1/2 times base times height. Take a look at that base right there. That is 5, right? So it's a horizontal distance to go from this lower left point to the point right at 3. And this horizontal distance, if the y coordinate doesn't change, you're just looking at horizontal distance. You always just do bigger x value minus smaller x value. It's a thing we looked at back in optimization. So 3 minus -2, that's 5. And then the height also happens to be 5. That's why we found the y coordinate that we did right here. So this is a 1/2 times 5 times 5 area. And then the other triangle in yellow, take a look here. This base across there is 10, right? Because it's 13 minus 3, or 10. And then the height is 10 because that's why we bothered looking at what the y coordinate and putting that tick mark of 10 was for. So the bigger positive area is 1/2 times 10 times 10. And so putting this all together, the two areas. So the original question, just to illustrate how this equal sign works, I copied the original question down here, and then there's this area, there's this area, both are positive, so no minus signs in reporting the area. Does this look okay? I feel like I was blabbing, but I just wanted to make sure. I think conceptually, the main thing that comes up is just stuff related to how did the graph look the way it did, but I just shifted over the traditional absolute value graph 3 units to the right. If you don't like that, I mean, this function isn't, I mean, there are definitely more complicated functions out there in the world. So this doesn't have too much stuff. So in principle, you could just start choosing x and y values, but you would need to choose enough x values, probably something around 3, right? So 3, so 1, 2, 3, 4, 5, then you could see kind of this action going on and graph based on that as well. It's not what I would recommend because it's a little more time consuming, but in principle, you could do that to get this shape as well. Are we doing okay with that? What I want you to do, unless there's questions, is I would like you to take the next 15-ish minutes to try as many of these as you can stomach here. So sorry for these link things getting in the way. You can look at the links now or later if you'd like, but there's a problem, and then here's another one. And in all of these are all about signed area right now. Tomorrow we'll have a new way to look at most of these. Not even all of these will work using tomorrow's method, but to make sure we understand what the heck this is really originally representing, I'd like you to draw, right? So like, let me circle, the function in each case. Right, draw the function. The last one, when you get there, the hint is to think about a circle first. But anyway, I would say just start in order. Draw the graph. Draw in the 2x values, like 2 and 12, or like 4 and 10 in the third example. See which regions are above the x-axis, which are below. All the shapes you have, at least in these first 6 problems, should consist of rectangles and triangles. So use your area formulas. And there's 2 ways to think about problem number 2. So I tried to write about both of them and provided links to the 2 different ways to think about it. And we'll talk about these in a bit. And if you have questions, feel free to ask. How are we doing on the first one? Let me just, I'll draw a little sketch picture here. X and Y axes. X coordinates of 2 and 12 were provided by the problem. This function is just y equals 5. So that's the graph. It's going to run into the. So the graph is a completely horizontal line, right? So then the region we're talking about is this rectangle right there. Has a height of 5, has a width of 10, right? 12 minus 2. So the final answer to this question ought to be 50, right? So this should equal 50. I have, for people's reference later, when if you clicked on that first link, it would take you to a thing that looks like this. So kind of all the pieces are here. You don't have to look at all of this much, but maybe the text, sometimes there's a little quote thingy here, and there's text that I tried to put in to make it helpful of, yeah, rectangle has a height of 5 and a width of 10. So just make sure we were kind of on the same page with that first one, and then, sorry for the interruption. this second one just to talk through sort of the two options, and there's not like a, view. You can view it as a rectangle plus a triangle plus rectangle, or you can think of it as a big triangle minus a smaller triangle. Either way is fine, as long as you keep track of what it is that you need to be doing. So you've got this y equals 5x, right? So you've got line with a very steep slope. I mean, steeper than my picture. That doesn't really look like 5. That slope looks more like a 2 maybe, but it works. It'll be enough for the picture. It's x coordinates of 2 and 12 are provided, so 2, 12, and we will need these y coordinates over here and there. Those will help us out. So sorry if this is not quite to scale here. The function was 5 times x, right? So y equals 5x. That means we should have y coordinate of 10 here. And when you plug in 12 into 12 times 5, right? I think you'll get a 60 there. So the region you're trying to find the area of is this. And you could, split it right there. I'm trying to draw in that a little thicker. Sorry, this is not ideal. And you can see, so below that thicker drawn line is a rectangle. It's actually technically a square. And then there's a triangle above. So that's one way to view it. Or this bigger triangle minus smaller triangle idea would be like there's this big triangle kind of on the outside here. But then if you count all this, that's counting too much. There's this region right here that got shaded that shouldn't have been. I think it'll be a little easier if I just pull up this demo. So it was loaded. There we go. All right. So the region that we're looking at is this one shown here in purple. This is to scale, so now you're really seeing that slope of 5 business. But one way to view that purple region, let me turn off the coloring for that region. So notice this region is missing here. But you can call it this red rectangle. It's technically a square, and then this orange region separately. So there's the red region, and then there's the orange region, and those two together end up being the purple region. So you can add together the area of the square down here, which is 10 times 10, add that to the area of the rectangle, which is 1/2 times, and then the base is 10. And I hope this height of 50 makes sense. Now the y coordinate up here is 60, but the height of the rectangle, it's here just down to right there, to where this point 12 comma 10 is. And that height, the x coordinates are the same, so the height there is bigger y minus smaller y, so 60 minus 10. That's where this 50 came from. But the other way to view this, and it's some people prefer this, you can view the purple region again here as instead of thinking of that, look at the big triangle. So now I'm starting at the origin. There's this big triangle, but this big triangle is kind of a problem because it's more than the region you want. There's this little triangle over here. I'm trying to highlight those vertices right now that we shouldn't include. So I highlighted that in a new color. We need to not have this triangle, and I hope it makes sense that we're subtracting it even if it's above the x-axis, because we're just trying to cut out some of the area. So if you don't mind, I'd like to take a look at number 7, the final one on this list. The hint is x squared plus y squared equals 25 is a circle. So I'd like to actually start with that piece of information. This one's a little kind of obscure or strange at first, but I hope it reminds you of some features of algebra, even if they're a little kind of rusty. So starting with x squared plus y squared equals 25. This really is a circle. The radius of this circle is 5, right? So the picture of this, circle centered at the origin, radius 5, looks something like that. 5 there, 5 here, -5, -5. Um, the hint here is to solve for y in this, so let's subtract x squared on both sides, and you'll have y squared equals 25 minus x squared. And then when you square root, to solve for y here, we do need to square root both sides. You have y equals, technically when you square root, you have plus or minus. So plus or minus root 25 minus x squared. It's a common error for people to just try to distribute the square root sign, but you can't do that when you have a minus. Now the function we have, y equals root, this is only the positive part. So even though there's two pieces here, the part that we want is y equals root 25 minus x squared. So what does that look like? That actually, that's the top half. So if the y coordinate has to be positive, we're talking that half only. So that's the graph of this. And in fact, because the radius is 5, we have these x coordinates of -5 to 5. So the question being asked over here is actually, so between the graph of the function, that's the top half of this circle, and the x-axis, so between those, and then between x is -5 and 5, but that actually, we've already capped off already anyway. So this shaded region, how much is that? And here's where we need the area formula for a circle, right? So this, the area of a circle, we looked at this back when we were looking at optimization, was pi r squared. So pi times 5 squared is the area of the whole circle. But then we need half of that. So you take that and you divide it by 2, or you multiply by 1/2, either way you want to say it. Right? So I'll click on this. I thought I had it open here. Yeah, there it is open. Okay. So the point here is there is the full circle, right? So that's drawn in red here, but we actually don't want the whole circle. So when you take this, and the same algebra steps are being shown here, you square root both sides, you have this plus or minus sign, but we were only asked about y is plus square root of 25 minus x squared. And so that's what's shown here. And if we want the area, this is half of the circle of radius 5. So the area should be half of, right here, half of pi times 5 squared. A common error is instead of taking the area of pi times 5 squared and then dividing by 2 or multiplying by half, sometimes the error people make is they'll cut the radius in half, but this is still coming from a circle of radius 5. If you do that, so sometimes people change the radius and they'll say take the original radius of 5 and divide by 2, and if you have 5 halves as your new radius and you square that and then multiply by pi, that's the area of an entire circle of radius 5 halves. We want half of the area of a circle of radius 5. All right, so are we kind of overall okay? Questions I can answer before looking at one last thing for the day? Okay, I would like to, so having practiced that these definite integral thingies, so this integral symbol from the past was always antiderivative for us, but now when there's these numbers here, the thing that we're talking about is a signed area. There are certain properties. Now you don't have to, go around memorizing all of these, but some of these will be actually very useful in an upcoming web work. First of all, let's talk through some of these. This first property right here, it seems so strange, but how do we get 0? Well, take a look. You have a function. It doesn't even matter what function. So I've drawn down here some function, just kind of in the form of a cartoon. And you normally have two different x values, right? Like in the next integral down here, you have an a and then you have a b, and you draw on those two vertical lines. But take a look here. The key thing to notice is you have the x value a and you have the x value a again. So there's, down here, if it would draw, okay, there we go. So if x equals a is right there, and then that's where you start, and where you stop also right there at x equals a. That creates a very thin rectangle. I mean, so thin that the height is whatever is given by f of x, but the width of that rectangle is 0. And so you don't have any area. That's where this 0 comes from. The next one is a little strange. It doesn't have a good geometric interpretation, unfortunately. But if all you do is you just swap where the a and b go, so if the a is up there now and the b is down there, you just swap the two numbers there. That can be done, actually. And this sounds all strange that we could even do this at all, because normally the smaller x value is down here. But if you, for some reason, need to swap these things, you can do that at the cost of introducing a minus sign. The next one, we actually saw a property very much like this for the indefinite integral, where when you have a constant k times a function, you can bring the constant out in front. So we did a lot of that when we were anti-differentiating. The same overall deal happens here for definite integrals. The next property, we saw a property like this for the antiderivatives, or for the indefinite integrals again. So the integral of a sum, you can split it up as two separate smaller integral problems, and same with a difference. When you have a minus, you can split it up. The last property seems a little strange, but I'd like to draw a little picture to help represent what that one's about. So this fifth property, the overall idea is, again, you have a function. I'm just sort of in cartoon form drawing a function here. And it's most helpful to think about why property 5 would be true by just picking three x values, a, b, and c, just in order. So left to right, a, b, c. So then the left side, again, this for any of these properties to make sense, you got to go back to what the heck this thing means, right? This is an area. So this is the area under the curve y equals f of x, but above the x-axis. So this is the area under the curve, starting at x is a and ending at x is c. So that's starting here. I'm thickening that line a bit just so you can see where I'm pointing, and ending here when x equals c. So how do we, what's a way to get that area? You can cut it into two separate areas, here and here. So this plus that. So first of all, you have the area from a to b, so that's this first part. And then over here, you have the area from b to c. That's the next part there. So that's, this fifth property especially looks so bizarre as written, but if you can keep in mind this picture and keep in mind what this thing means, then I think the property is relatively natural. What I'd like to do, though, these seem a little abstract just presented like this. I want to demo a problem, or actually two problems that use many of these properties so that you can see kind of how this fits together. So this, this question down, so I wanted the property still on screen. Sorry about it being all the way down here. But this is a kind of a very, there's WebWork questions that look a bit like this, that I'll give you a chance to practice these kinds of properties. So if you see a question like this in WebWork, come back to this slide, for example. So you'll find things where like they didn't even give you the function. Like take a look at this question. They just say that some function, they don't even tell you which. Taking that function and looking at the area from 2 to 7, from x equals 2 to x equals 7, that total area ends up being 10 square units. And then they give you a question like, now find the integral from 7 to 2 of 3 times f of x dx. So again, the function isn't provided, but this information of 10 will be useful. So how will that be useful? Well, one of the things to notice is, look here, the 2 is down here, the 7's up there. Now the 7's down here, the 2's there. So I think the second property about swapping endpoints is going to be useful for us. So here's how I'd like to do it, just to keep the work as organized as possible. There's actually several ways to get through this. It's just a matter of which of these formulas up here do you use in which order. But I'm going to go ahead and just to try to make this kind of work here without getting to point as easily to things, I copied down the question, the thing we need to find, and I went ahead and started by swapping the the location of the 2 and the 7. And as this property 2 says, in order to do that swap, you just need to introduce a minus sign. So what are the changes from here to here? It's the 2 and 7 have switched locations, and then there was a minus sign that was inserted in front of the integral. In the next step, what I'd like to do is use property 3. So first of all, I'm going to copy the minus sign first. Okay, minus sign copied first. Just copy it. And then this 3 is like that k right there, and it can come in front. So if you do that, you should have a thing that looks like this. Again, the minus sign was just copied first. Just copy the minus sign, and then this 3, instead of having the 3 just to the right of the integral symbol, the 3 is written just to the left of the integral symbol. So take a look at where the 3 moved. And the whole point of doing all this is now take a look at this part right there. That was the information we were provided. We were told in the first part of the question that that's equal to 10. So I copied the negative 3 and I highlighted this step in red. The thing in red here got replaced with the 10 that I drew in red there, because that was information we were given. So ultimately the final answer to this one is negative 30. Hope that's kind of okay. I'll just pause and see, are we okay with that? Is there a step that we can kind of rehash through? Okay, then one more. So this question was a version of this. So I hope by demonstrating some of these, you kind of see how these other ones might work out. But for the next one, so in this one, we were given information without even being told the specific function. In the next one, I've given a specific function. So there are the properties up there again for reference. But now the question is integral 5 to negative 1 of 4x dx. Now, this is strange because normally when given the function, so far in all the examples we had today and yesterday, the smaller x value was down here and the bigger x value is up there. And you need to have that in order to think about signed area. So actually, the reason I picked this specific problem is the first problem we did today was we did integral from negative 1 to positive 5, those x values in that order, negative 1, the smaller one down here, the bigger x value up here, of the function 4x. And our answer to that was 48. That was the one that we were like, wait, was the answer 38? Or, some arithmetic thing happened. So I just want to, the point is, since we already did all the hard work, I don't want to redo more work right now. I wanted to borrow the work we've already done and focus on these. Now the question is integral from 5 to negative 1. Well, so these, all this is the same function, 4x. We just have to do this swap. So that's property 2 again. In order to swap, you've got to insert a minus sign. So if you take this negative 1 and 5 and you switch the locations, then instead of a positive 48, we'll have a negative 48 as answer. So we already saw this swap business providing a minus sign when the function f of x wasn't even provided. And we're just applying the same property 2 in the case of the function, applying property 2 in the case of the function being provided. Okay, all of this stuff with definite integrals, definitely it requires a bit of practicing things with graphing of functions. Fortunately, the kinds of shapes we're going to be using when looking at computing areas in this format use familiar area formulas. So triangles, rectangles, and circles. Okay, I just want to remind you that there's, for the sake of Thursday's exam, there's indefinite integrals on it, but not definite integrals. Now I know, like, no, this always seems to happen, but it would have happened no matter what the cutoff of topic is. There's always new stuff relates to old stuff, so we just need to sort out that this kind of stuff, this kind of thought process would be part of exam 4, and this part will be sometime after exam 4. Um, the difference is seeing the endpoints written. The final answer here is it's an antiderivative plus c, or a function plus c. Over here, the final answer ends up being a number. That number represents signed area, like the area of this triangle. Now these seem like so different, right? And I get that. And uh, the whole point of tomorrow's class shows us what the link is. Without what we do tomorrow, which is called the fundamental theorem of calculus, it's a fantastic topic, but without that connection, this notation being so similar is ridiculous, actually. But because of the connection, um, it makes sense to use similar notation. I will comment um, that tomorrow what we're going to do is we're going to compute answers to questions like this. We'll get numbers like that without even using area formulas, but it's important to remember that this always represents an area. With that, I'll just do the same announcements from the beginning. It is a Tuesday, so please complete the online quiz. There is the due on at the end of Wednesday. There's the math is a process assignment, so please turn that in. It's meant to be a short assignment, and we will not have a live class Thursday morning. That is the official date of the exam, but you pick your own 5-hour window of time. Between Thursday and Friday, you pick your 5-hour block of time and work on the exam. I only want it to take you an hour-ish. I don't want anyone to use all the time. That's not really the point. But the time is there just so that you don't have to stress about things. And the key format difference is one PDF file, please. So with that, we'll end a little early today, unless there's questions or something I can address.